morning everyone, this is Ken Jasper B, and today we are going to report the Chapter 7, Introduction to Heat Transfer. Under this chapter, we are going to explain the electrical analogy for thermal resistance. The electrical analogy of thermal resistance treats heat transfer like electrical current flow. Thermal resistance, which opposes heat flow, is analogous to electrical resistance, which opposes current flow. Temperature differences act like voltage differences, and heat flow is analogous to electrical current. This analogy allows engineers to use electrical circuit analysis techniques to solve complex heat transfer problems. This analogy allows us to represent heat transfer through various materials or components using equivalent thermal circuits, similar to electrical circuits. For example, a composite wall with multiple layers can be represented by thermal resistance connected in series, allowing for easy calculation of the overall thermal resistance and heat transfer rate. Discontinuous conduction medium, or DCM, is a mode of operation in power converters where the inductor current or capacitor voltage ripple is high enough to cause the applied switch current or voltage to reverse polarity, leading to a period where the current through the inductor drops to zero during the switching cycles. This differs from continuous conduction mode CCM, where the inductor current remains positive throughout the switching cycle. A continuous conduction medium refers to a material or system where electrical current flows continuously without interruption. This contrasts with discontinuous conduction, where current flow is intermittent or ceases for a period of time. In electrical circuits, this often refers to the inductor current in the switching regulator, where continuous conduction mode CCM means the inductor current remains above zero throughout the switching cycle. In essence, DCM represents a specific mode of operation in power converters characterized by a discontinuous inductor current and significant changes in the converter's behavior compared to CCM. In CCM, the inductor current remains above zero throughout the entire switching cycle, meaning energy is continuously transferred to the load. In DCM, the inductor current drops to zero for a portion of the cycle, resulting in a discontinuous energy transfer. Electrical circuit theory can be used as an analogy to analyze heat transfer problems. This analogy equates electrical current to heat flow, voltage to temperature difference, and electrical resistance to thermal resistance. This allows complex heat to transfer scenarios to be modeled and solved using well-established electrical circuit analysis techniques. In this analogy, temperature difference is analogous to voltage, heat transfer rate is analogous to electric current, and thermal resistance related to material properties like thermal conductivity and geometry is analogous to electrical resistance. This allows for the use of circuit analysis techniques to solve complex heat transfer problems in systems with multiple components or layers.
Let's now proceed to the composite wall. So the concept of a thermal substance circuits allows ready analysis of problems such as composite slab or composite planar heat transfer surface. In the composite slab, the heat flux is constant with X. The resistances are in series and sum to RTH equals RTH1 plus RTH2. If TL is the temperature at the left and TR is the temperature at the right, the heat transfer rate is given by Q equals delta T over RTH equals TL minus TR over RTH1 plus RTH2. Okay, so let us now proceed to the overall heat transfer coefficient U. So the formula will be Q equals TA minus TV over 1 slash H1A plus delta X slash Ka plus 1 slash H2A. So the 1HA represents the convection resistance and the delta X slash K represent the conduction resistance also. So the overall heat transfer, which is the conduction plus convection, can be expressed in terms of an overall heat transfer coefficient, U defined by the relation of Q equals UA delta T, and A here is the area for the heat flow. And the overall heat transfer coefficient is equals to U equals 1 over 1 slash H1 plus delta X slash K plus 1 slash H2. So U also related to the R value, which is U equals 1 over R value, wherein the R is equals to delta T over Q slash A. So this formula is for AI and AO, inside and outside surface area of the inner tube. So this is the overall heat transfer coefficient for hollow cylinder based on the inside area of the tube A and the outside area of the tube AO. So lastly, the general notion, plane wall or cylinder coordinate system, is that UA is equals 1 over E RTH is equals to 1 slash RTH overall.
In conclusion, the electrical analogy for thermal resistance is a useful tool for understanding and solving heat transfer problems. It allows us to treat thermal resistance, heat flow, and temperature differences in a way that is analogous to electrical resistance, current, and voltage. This analogy simplifies complex heat transfer calculations, particularly in systems with multiple layers or components, by enabling the use of electrical circuit analysis techniques.